Welcome back to the classroom. My name is Mr. Wong. Today we'll be looking at the 2004 HSC physics paper, question 21, and it's worth 6 marks. So this is actually to look at module 6, inquiry question number 4. Our very first question of this exam paper is, the diagram below shows a two-pole DC motor as constructed by a student, as you can see here. In the question we have, the very first one, it says, identify 3 mistakes in the construction of this DC motor as shown in the diagram. So there's a couple involved here. If we actually have a look, firstly, with the commutators, the brushes, it's not connected to a power source. So if that's the case, then obviously we have an issue of no supplied EMF going into our motor. So the brush is not connected to a power supply. The second issue we have is that our split ring commutator is not linked with the coils of our motor. So no what we can say, electrical connection between coils and commutator. So that's one of them. The next one we have is the size of our coil, or the size of, we call this section here the rotor, with the size of our magnet. So if you actually imagine, if I over here draw it right now, this is the side-on view of what we see here. However, if it rotates 90 degrees, it will look somewhat like this. Now, you might recognize, or some of you might not recognize, the issue of this rotation. So part of this rotor is actually out of orientation. So what we have here is when the actual rotor rotates, the majority of the coils that are there will no longer be exposed to the magnetic field. So we can say that the rotor is too large, and when it rotates, not exposed to the B field anymore. So that's the third one. We can actually look at a couple more examples because I just want to highlight them all out. Again, just keep in mind this question is identify, so if you list it out, it's more than okay. But let's go a little bit more and actually talk about why it's an issue. So here we have the Y's. If you have a look at the Y's that we have here, if we actually look at how the wiring is going, this is going in a sort of, if you look from the side-on view from this side, this is in a clockwise direction, while as this one is wide in an anti-clockwise direction. So what we can say with the coils is the two sides are wired in the opposite direction. Why is that an issue? If I look at here, let's assume that the current is going through here. Okay, using my right-hand palm rule, magnetic field is going in this orientation, so we're pushing up. Okay. If I look at the orientation, imagine the lines are cutting through down below. Okay, so if the current goes through, it goes up here, through here, and then down this straight here. So it's going in this orientation down below. So what's actually happening here at the bottom part of this wire, it's also exerting a force pushing up, okay? So because it's pushing up from the bottom and the top here, you have a scenario where it looks like it's pushing up here and the bottom is pushing up. So we're not getting that rotation on our motor, and that is obviously an issue. Okay, so that is the reason why having them in the opposite directions is not a good idea for the construction of our motor. If we look at some other examples, we can look at the orientation of our split ring commutator. So in order for this to actually work, this split ring commutator should be rotated another 90 degrees around. The reason being is what we have right now is, if you imagine the split ring commutators and our brushes, when it rotates once, they come here, okay, it's not going to work because once they get to one part here, one part there, they might not be touching with our brushes. So they need to be rotated at 90 degrees as soon as contact is made with the electric circuit. If there was an electric circuit, the second or the front part of the split ring commutator, as it rotates, it's already touching the next brush, and so they can continuously rotate. So we need the split ring commutators rotated another 90 degrees in order for that rotation to work. Okay, and then the last one, as you can see, our plane of coil is stacked vertically to the actual motor, or the actual magnet, sorry. So if we said over here the current was going in this direction, the current is going the opposite direction down here, and vice versa, like so and so. So there's a continuous cancellation of the forces around the coil itself. What we should try and do is create a coil where the plane is horizontal to the magnetic field, or we can say the area vector is perpendicular to the magnetic field. So those are all the different types of issues that's affecting this motor design. So as you can see, there's at least 6 reasons we can come up with. So let's just write them down. So we could say number 1, no external power supply being connected to our brushes. Number 2, we have no wires connecting the coils with the split ring commutator. Our third one that we are going to mention is the windings, or the windings of the coil on both sides of the axle, which is the middle component. So this is our axle here, is wired in the opposite direction. So are in the opposite direction of each other. So that's number 3. We did talk about 6 reasons, but I'll just put 1 more. So we'll have 4 reasons in total to talk about. we can say the orientation of the coil is too big, and as it rotates, parts of the coil are no longer in the magnetic field. And so that's how you do part A of this question. Okay, let's move on to question B, which is the last question here. So with question B, we have an ammeter was used to measure the current through a small DC motor. While it was running freely, the current of 2.09 was recorded while the motor was running. The axle of the motor was then firmly held, preventing it from rotating, and that's when we recorded a current of 2.54. So explain this observation. Okay, so what's happening here is we are obviously preventing a change in flux, and by holding this axle here, we're preventing it from rotating, so preventing change in flux. And obviously, as a consequence, if there's no change in flux, there is a reduction of EMF being produced, back EMF that is. And so that would increase our net voltage. So let's try and put that in words. So as the axle was prevented from rotating, this meant that there was no change in flux. So if there is no change in flux, according to Faraday's formula, so Faraday's law, according if the change in flux is decreased or reduced, so that all goes to 0, then the back EMF also goes to 0. Okay, so that there was no change in flux, hence decreases production of back EMF and so because the net voltage is essentially our supplied EMF subtracted by our back EMF, the net voltage will increase and therefore the net current, which is the net voltage over resistance, that's constant, and this increases, the net current is increased in the motor. So that's why we see it go from 2.09 amps to 2.5, what was the number? 54 amps. So that's how you answer the question. If you found this explanation useful, hit that like and subscribe button and I'll see you next time.